All right, so hi again, everyone. I hope that you're all doing great. And welcome to the second talk of AI Summit. This one is titled A Tale of Foundation Models in Tiny Hardware. It will be led by a very special guest, hadjer benmeziane, a PhD student at Université Polytechnique Hauts-de-France, and also the founder of our dear community, School of AI Algiers. Feel free to ask your questions whenever you want, and now you can start, Hadjer.
All right, perfect. Thank you very much. So for the invitation, I actually was with Wedgie talking with the manager of School of AI. So I guess I kind of invited myself. But yeah, thank you for organizing such a beautiful event. And I'm really pleased that School of AI Algiers is really doing great, especially this year. It's really great. Okay, so yeah, the talk that I'm going to present is called The Tale or Story of Foundation Models and Tiny Hardware. And we're going chapter by chapter, trying to understand each step of it. Of course, as Lena said, you can ask me a question at any time. I hope I can check the chat, yeah, and of course answer these questions. Okay, so let's start with chapter one. Chapter one is deep learning revolution. So as we all know, deep learning is used in different domains. So we have seen this video of Boston Dynamics with a robot jumping or robots dancing. We have seen Tesla autonomous driving car videos driving around San Francisco and really getting understanding like where to stop and when to do it. We also have seen like some deep fake video trying to reproduce or talk in the place of the President Putin or even the presidents of the Ukraine for the with the recent advances in the war. And also we have seen like some AlphaFold so AlphaFold is a model that tries to combine like protein folding, understand protein folding and understand how a protein will fold in the future. So predict this. And of course, I didn't talk about style transfer, as you can see here with Maqam Shahid, or the game of Go, where like DeepMind achieved or beats one of the biggest players in the game of Go. But actually, what's deep learning? So we hear about artificial intelligence, machine learning, deep learning. I know I always start with this question at the beginning of my presentation, and I hope that now everyone knows it, the difference between all these three terms. But yeah, let's just keep it simple and we describe each concept. So basically, artificial intelligence is making a machine decide by itself. Whatever task it does, if the machine decides by itself, then we call it artificial intelligence. And then inside artificial intelligence algorithms, there is one algorithm that is data centric and that uses machine learning. So machine learning understands or try to take decision by trying to find some patterns in recent experience in old or data set that we already have. So basically we have a data set, we try to find the patterns, and then I can decide by myself in the future. And here I is the machine. And inside machine learning, so we have this concept of learning from the data. Inside machine learning, we have deep learning. So these types of algorithms are brain inspired. So they are inspired from what we have in the brain and neurons, synapses, and how everything is connected, but it is artificial. So actually, we created some sort of neural network, artificial neural network that connects different nodes and applies some specific operation. It's all mathematics, so it's all like understandable, but we know that this kind of neural networks are learning the different tasks. And thanks to them, we achieved like these applications that I'm talking about, a robot jumping, an autonomous driving car, etc. So now the question, like, why is deep learning like so good? So at the beginning of 2012, we had this paper published, which is ImageNet classification with deep convolutional neural networks. And this is a really pioneering paper. I think if you didn't hear about the paper, you certainly heard about AlexNet. And AlexNet is the product of this paper. And basically, this paper proposes like an architecture and also a training paradigm that beats all different machine learning models on the ImageNet class competition. So there was like a competition that tries to do image classification the best way possible and to have the best accuracy possible. And back then in 2012, the best models were machine learning models. And when we say machine learning models, it means not deep learning. So classical machine learning is more like boosted trees, some random forest, etc. So these ones, or a very simple neural network. So these are like standard machine learning algorithms. And this is what was applied back then in image competition. And the real goal was behind like, how can we extract the features from an image that will help us to classify that this image is a dog and this image is a cat and this image is a computer and this image is a desk, etc. So basically this is image classification. And when AlexNet came, so they defined the standard convolutional neural network that we know of now, where we have a convolution, then ReLU, some activation function, and then a pooling, another convolution, another ReLU, another pooling, etc. And this definition of convolutional neural network has already been published like several years before in the 80s, 90s, and end of 80s, beginning of 90s. But the thing is, in this paper, they proposed a training paradigm and a training way to achieve a really good accuracy on this competition. And from 2012 and on, the beginning of the race and of using deep learning began. So people understood that now, okay, now maybe we won't focus on which operation we're going to use. Are we going to use the convolution or the pooling or this? No, we're going to focus on how to combine these operations together in the best way possible. So am I going to start with the activation function and then convolution? Should I add a batch normalization at the beginning or in the middle? And should I use pooling every time I do the convolution, or maybe like do the convolution 2 times, 3 times, and then use pooling? So this paper was a real pioneering paper that came, and everything that came afterwards was like a combination of how can we combine these different blocks or these different operations that we already know of, but how can we combine them in the best, in the best possible way? And here comes like a different variety of deep learning architectures. So we have convolutional neural networks. Now we hear about transformers a lot. We have implicit layers and neural computers. So we have different types of neural networks and so I think you hear about convolutional neural network a lot. With this convolution operation, they mainly apply a convolution operation to extract the features, to automatically extract the features, and then at some point they apply a pooling layer in order to reduce the size of the feature map. And at the end there is this fully connected. So here when we say subsampling, here in the middle, it's the pooling layer that reduces the size of the feature map. As you can see, we have a feature map that is quite large at the beginning, and then it goes down and down and down. And at some point, we have one fully connected layer that merge everything and give us the output. So this is the standard convolutional neural network. But what is out there actually, we have different types of operations that came from 2012, of course, and a different kind of structures, different kind of models, etc. So in the transformer block, the transformers are mainly using one operation that is called the attention. And the attention operation was actually used for NLP, for natural language processing. So of course, you know that deep learning is not only used for images, it's highly used for analyzing text, understanding text, etc. So one of the models that was out there before transformers were using this recurrent neural networks. So recurrent neural networks are suitable for sequence data, and sequence data are like text data. Text data is the best example for sequence data because you have one word, then another, then another, another, etc. Another example of sequence data is the speech. So when I'm talking, I'm also saying something and then something. There is time inside this, the idea of sequence data. And then so we use like recurrent neural network in these kind of data, because recurrent neural network have this kind of no, each layer is also connected to itself to get to the other words, etc., etc. So it has some repetition. So for example, to predict let's say a sentence, any sentence we can think about, let's say I have a dog. So to predict have after I need to know that I predicted I before, and if I have, then to predict I need to know that I predicted I and have before. So the informations that are coming from the same layer are repeated and are used to generate to generate the next words. But the problem is that they needed some sort of attention operation, and the attention operation adds this idea of remembering long distance word. So when I say I have a paragraph and I say I have a dog, this dog is named blah blah blah, and sometimes I will like talk a lot and then say it has 4 legs, and I need to know that this it refer to the dog that I talked about at the beginning of the paragraph. So basically the purpose of the attention operation is to overcome this problem. And at some point, so they were using recurrent neural networks, but in the middle, the attention operation. So it's like using convolution, and then in the middle, we have this pooling operation. And it's the same thing that was happening before the transformer came. We were using these recurrent layers, and in the middle, we had the attention operation that can tell us which words are important and are connected to each other. And then there is this paper called "Attention is All You Need," or "All You Need is Attention," one of it. I always like mix it up. But basically this paper, "Attention is All You Need," is using only, define a model that only used attention. And they call this model transformers. So it's what you can see here. So we have this self-attention and then some fully connected, some feed forward, and then self-attention, feed forward, self-attention, feed forward, and a linear layer at the end. So it's only using the attention mechanism. It's not using anywhere a recurrent layer like LSTM, GRU with different cells. And then we also have these neural computers. So neural computers are differentiable neural networks. They have like they include the memory in the neural network. They are interesting, but however, they are not really used in all applications. But nowadays we can see them more and more, especially in what we call neural architecture search that I'm gonna define afterwards. So just to give you an example of an architecture, a deep learning architecture. So there's the difference between a deep learning architecture and a model. A deep learning architecture is the sequence of operation that we execute and their hyperparameters. So if I say, okay, I'm going to execute a convolution, then a ReLU, then a convolution, then a pooling, and this convolution has a 3x3 kernel, the other convolution has a 5x5 kernel, etc. I'm defining the architecture of my model. And usually the model is the final is the final product. So if I say ResNet, for example, it's a well-known or standard model that is used for image classification. If I say Vision Transformer, it's a well-known also model that is used for image classification. If I'm talking about SWIN, it's another model that is used for object detection, etc. So if I give a name to my final product, it's a model. So it is something that is already trained, that already has an accuracy, etc. And if I'm talking about the architecture, so I'm talking about the sequence of operations that is executed. So this is what we are defining here. So we're defining the architecture of a convolutional neural network. It begins with an input. Usually the input in a convolutional neural network is an image. It can be text. Convolutional neural networks have been used for NLP too, but usually we use them for images. So let's say the input is an image. And then we have a first block. And in this block, we can have a convolution, a pooling, a depth-wise convolution, a grouped convolution. So we have different variants of the convolution that we can have. And we may have like another block attached to it that applies a different operation, a third block that is attached. So here is just an example. I'm using 3, but it can be like 100, it can be 2, it can be just 1, but it can be like a really big number too. But basically in each case, in each block, We can have a convolution, we can have a pooling, we can have different variants of the convolution, we can have different operation. And each of these operations can have an architecture, a set of architecture hyperparameters. So this is what I'm defining here. So when we talk about what is the architecture of ResNet, so I'm asking for the list of operation per layer, what operation is executed per layer, and also what are the hyperparameters associated with this operation. So if I'm using a convolution in layer 1, I need to say what is the kernel size, what is the stride, what is the padding, etc. And then, of course, we have this kind of fully connected layers. And in the fully connected layers, we need to know the number of units per layer, etc. And we also have, at the same time, training hyperparameters like learning rate, momentum, batch size. So to sum up, what I wanted to let you know from this slide is the fact that if I am a machine learning engineer and I need to create a model for my data set, I need to tune or to test several architectures, and inside each architecture I need to test several hyperparameters and several operation per layer. And also once I do that, I also need to test several training hyperparameters, learning rates, momentum, batch size. So it's really frustrating, and from a machine learning engineer perspective, it's kind of impractical to test everything. So usually in a few years back, the machine learning engineers would build a really high expertise, and that could tell them that, okay, I have this data set. Usually in this data set, because I have this number of output, then I'm going to use directly this architecture with this learning rate, with this momentum, etc. And usually when we are like, for example, okay, I'm in the image data set, so I'm going to use RMS prop because I know that this optimizer is better. If I'm like in training for a natural language processing, okay, I'm going to use ADAM because I know that this optimizer is better. But it's not like a real implication. It's not like a proved implication. It's just like from experience, I know that this is better for these tasks, etc. So it's really hard to define the architecture and the training hyperparameters and everything that goes around it. Okay, so now let's go to chapter 2, which is called The Bigger, the Better. So in conclusion of chapter 1, we know that there are a lot of architectures out there, and these architectures, from a machine learning engineer perspective, we need to tune a lot of things in them. So it's really hard to build the perfect architecture for a given data set. So chapter 2 is called The Bigger, the Better. Basically, we're going through different models that are called foundation models now. And you will notice why we call them foundation models throughout the examples. I'm going to start with a massive language model called GPT-3. I'm sure you've heard of GPT-3. Maybe you've heard of ChatGPT now, but let's start with the basics and start with GPT-3. Just checking if there is any questions from the first chapter. Okay, in machine learning, how can we test all the parameters? Okay, so I think you mean like hyperparameters and not parameters, because there is a distinction. Like parameters are usually the weights of the model, and hyperparameters are usually what I defined here. It's like the list of different hyperparameters that are associated with an operation or with the architecture, so we need to tune them. There are several methods to do that, and we're going to discuss one at the end of the at chapter 3. But basically, before, what we were doing is intuitively saying, okay, I'm going to try the learning rate 0.001 and 0.01 and 0.01 because it's logarithmic. So I'm going to try these and see what it will give me. But yeah, it was intuitive, and we give a list and we try everything and we see. But I'm going to show you like some examples at the end where we use optimization algorithms in order not to not to test everything, but be intelligent about it and test what really will give me like the best solution. Okay. I hope I answered your question, but if you have a follow-up question, please do. Okay, so yeah, well, let's start with GPT-3. Basically, GPT-3 is a really big transformer model. So we take the transformers like we defined them in the first in this slide, where we have this self-attention everywhere. We have the fully connected. We actually take only the decoder part, because we have here a first part. The left part is an encoder, the right part is a decoder, but we actually take only the decoder part. And we make it really big. And when I say really big, it means that we actually use the hyperparameter and try to make the most, the extreme cases of hyperparameters. So this model has actually 175 billion parameters. And it was trained on 300 billion tokens of words. So this is also a massive data set. And this data set was extracted from online, from online sources. So for example, this GPT-3 knows all articles in Wikipedia. So it was trained on all articles of Wikipedia. So if you ask him any question about something in Wikipedia, it will answer. Of course, the type of architecture, as I said, is a transformer. And it was trained with an unsupervised learning way. And by this, you can see it on this slide. You give it a sentence, and then it will predict the next word once at a time. So basically, you give it the whole sentence, recite the first law of robotics, and then it will give you a, and then you give it recite the first law of robotics and then it will give you robot, and you give it like word by word. It's actually token by token, but let's imagine the token is a word. So word by word, it will predict the next one. So you give it recite the first law of robots, and it will give you the third word of the sentence, which is may. Okay, so this is the unsupervised way, and the estimated cost was about 355 GPU years if we didn't do any optimization. So if we train it like we're doing now with PyTorch, like doing only a training, having this 175 billion parameters, it would take 355 GPU years on one GPU. And it's not like the worst GPU out there, it's one of the best GPUs. And it will take this number of this huge time. So it's kind of impossible to train it, but what they did is they come up with a strategy to optimize the training, to make it distributed, to train it on a huge cluster, and it costs $4.6 million. So it was really a massive language model that was proposed by OpenAI. Okay, I'm just gonna check. I'm like swinging back and forth between questions and the slides. So I want to know, when we are working on a company that need an intelligence, how can we try a lot of architecture, because they need results as fast as possible? Yeah, so this is a really good question. Actually, we live it even in when doing PhD. We want to have the results really fast, or when we are in a company, we have a deadline, we want to have the fastest possible model at the end. So let's just keep talking about foundation model, and maybe at the end you'll have the idea. So I think actually I answered this in the next slide. So yeah, so let's just maybe first have some examples using GPT-3, and then we're going to discuss like how can we do when we are in a company and we need a model really fast, like can we do it, and how. Okay, so the interesting thing that I tried is, what is School of AI Algiers? So just to remind you, this GPT-3 was trained on a massive data set, and this data set came from online articles and online actually everything that can be used and as a data set was used. So when I asked GPT-3 what is School of AI Algiers, so it answered School of AI Algiers is a learning community in Algeria that provides free online courses in artificial intelligence and related topics, which is really impressive. Like, we are not one of the biggest community out there, but at least GPT-3 knows us, so that's a really good thing to see. So yeah, there is this, I am gonna share this tab again. Yeah. So as I said, GPT-3 is proposed by OpenAI, and they propose this playground where you can ask different questions and GPT-3 will answer. So if you want to propose any question you want to ask, maybe we can do this live now. Let's see if you have any question you want to ask GPT-3, and we can see what's the answer. If no one has an idea, so maybe we can take Abdul Karim's idea here. It's how can we ask in a company context? Actually, it's more like a question for Chat GPT, but let's see what it gives. Okay, training a model quickly in a company context can be done by using distributed computing, leveraging cloud computing resources, and using automated high-parameter optimization techniques. It's actually it's a really good answer. So I'm just gonna check if you have any. Oh, what is EASY? Okay. Okay. What is EASY? Is like an acronym, but maybe ECOL. I don't know. It can be. Is a higher educational institution in Algeria that specializes in computer science and information technology. Okay, cool. What's weather today in Algiers? Okay. What's the weather like in Algiers? I don't know if it's going to respond correctly. It's not actually connected to, is it correct? 25 degrees and a low of 16? I don't know if it's correct. Let me know. Because it shouldn't be connected to like Google to get this answer, but maybe it is within this playground. But yeah, it gives like really good answers for each question you have. So yeah, to respond to Abdelkarim's question, we have these massive language models, and actually this is the use of foundation models. So this is the reason why people are trying to create foundation models. They want to encourage the use of pre-trained models. So they want companies to take directly these models and use them for their custom data sets. And so, yeah, in other words, usually when we have a custom data set in a company, we don't need to tune all these hyperparameters and try to find the architecture or the best architecture possible. We just need to take one of the foundation models, like GPT-3, and customize it for our data set. So one of the customization would be like to just modify the output so that it fits our purpose or it fits our task, or modify the input size and modify everything inside or something like this. So one thing I wanted to mention here with this figure is that from 2020, the size of the models got really big, and by really big I mean from 17 billion parameters until 530 billion parameter. And we also have the Microsoft one somewhere here with a 1,000 billion parameter, which is trillion parameter. So we have really big models, and it's true, it encourages the use of pre-trained models. One of the other aspects is that fine-tuning these models is not really necessary, because sometimes you say, okay, I need maybe to do some transfer learning, or maybe I need to fine tune this model for a few epochs so that it learns or it is really customized to my data set. And because these models were trained on a really huge data set, it is not really necessary to do that. And sometimes just taking this model and putting it into our data set and trying to solve the problem directly give good results. So maybe one thing you can try is taking different foundation model, try them all and see which one gives the best result and is it enough for my tasks. Okay. So in other words, it helps us having foundation models. It helps us save time for the companies. It helps us save money because all these, most of these massive language models and also foundation models are open sourced. So you can directly take them. Sometimes you have an API and it is, you need to pay for the API, but most of the time the architecture is out there. And if you have the resources, you can train it. If not, you can just fine tune these models for your task. And we save the hardware resources because we have one giant company that will train these models on a giant cluster, but then at the end we can use it in our hardware resources without training, because of course training will take like more training is more computationally expensive than just using a forward pass on the model or an inference. But is it really the case? We're going to answer that in chapter 3. Another exciting foundation models are for images. And I'm sure that you heard about these models. So we have Stable Diffusion, DAL-E, and Midjourney. Whatever model you heard about, it does the same thing. So it makes image generation and caption understanding more generalizable to anyone. Here it's the it's the description of Stable Diffusion. This is an open source model. DAL-E is now under the API of OpenAI, so you have some credits and you can use it if you have enough credits in your account. Basically, it does image generation, of course. It has a hybrid architecture, a convolution, and a transformer. So usually they use this CLIP model. CLIP model is a vision transformer model, and this CLIP model, or this part of the model, is responsible of basically understanding the caption or understanding the text and turning it into some encoding matrix so that the convolution or the encoder part will generate the image. It is a really large network with 860 million parameters and 130 for the transformer part or for the clip part. And here are 3 images that are generated with these different models with the caption astronaut on Mars, mysterious, realistic, and you get these things. And of course, you can have like Stable Diffusion is out there, so you can go and play around in the playground. I use this to generate this Yoda playing football, and you have this image here. Okay. Okay, so just getting back to the questions. So the job of data scientist is in danger. Oh, not really. We're still like, we're still working on the models, and we still need expertise to know which model or which foundation model is going to be used and how to fine tune it, etc. So still work to do in the data science part, and especially maybe the most important part of it is to analyze the data, to put them in the correct format, to know which kind of task I can do with the data or not is still a human task. Okay, and then Abdulkarim said, so as I understand, in the right way, because I have an image classification project, and we decided to train a pre-trained YOLO version 5 and version 7 on our custom data, or there is another known models to use instead. Okay, if it is image classification, I wouldn't go for YOLO version 5 or YOLO version 7. If it's image classification, then I would go for a simpler model like a ResNet-like model, or a simpler model than, so YOLO models are created for object detection and instant segmentation, and especially they are like end-to-end object detectors, so you can put them on small devices and stuff like this. But if you're doing only image classification, then I would suggest to go for a ResNet architecture and not complicate yourself with finding where the image, where the objects are in the image. But yeah, you're in the good, you're in the right way, in the sense that you're taking a pre-trained model and you're still working on it on a customized data set. Okay, another foundation model I want to discuss, as you may notice that all of these foundation models are from OpenAI. It's actually one of the things that is great about OpenAI is that everything is open sourced, and they have a really good communication service, because they communicate a lot about their models. It's good, and at the same time, there are other models out there that are really good. But Whisper achieved a great performance on trying to do text, speech to text, basically. So it was trained similar to all the others. It was trained on a really huge data set that contains 680,000 hours of multilingual and multitask supervised data. And it has different number of parameters. And what I mean by that, it has, so there is a version of it that is the base version, that is 74 million parameter, which is already huge. But it can go up to 1,550 million sorry, parameters. And also this architecture is also hybrid, where you have this convolution at the beginning just to understand the spectrogram of the audio file, and then you have this encoder decoder part, just like yeah, it makes you remember like transformer architecture, but basically you have the attention everywhere, and it helps you predict the next token in the speech. And similarly to all the other OpenAI products, you can go ahead in the blog and test it with some recording and stuff like this. So it's really great to try and test it. And it's really easy. Okay, let's see. Okay, there are no questions. Basically, now what I want to say is that there is this new model that is out there that is called ChatGPT, which is really, really impressive. So I tried different things in it. I tried to play with this model, and it gives really good results. So yeah, the whole presentation that I'm actually presenting was made or was created by an AI. And what I did is I said, okay, can you create the outline of my tomorrow's presentation? As you can see, I'm also like, I also work last minute, so I actually started creating the presentation yesterday. But basically, can you write the outline of my tomorrow's presentation on foundation big deep learning models and tiny hardware platforms? And the chat GPT was like, okay, right away, sure, here is a draft of the outline for your presentation on foundation models. And you start with the introduction, begin by introducing the topic of your presentation, blah, 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 explain the purpose of your presentation and what you hope the audience will learn. I actually didn't do that. I should have. It's a better advice than what I did. Overview of deep learning, give a high-level overview of deep learning, describe the key components, etc. So maybe you want to try it. So give me your ideas. What do you want to try? So what we tried this evening, this afternoon, I was in the lab and I was like playing with ChatGPT all afternoon. Basically, I said, write the manuscript structure for my PhD thesis on neural architecture search. What did I do? Okay, maybe I can do that now, but feel free to give me like some examples you want to try. Can you write the manuscripts? Thesis manuscript may be better. Thesis manuscripts structure for neural architecture search. It takes a little bit of time, of course, just to think. How about which country is more likely to win the FIFA? Okay, we'll do that next. But I think it will tell you, no, I cannot do that. I don't know. Basically, as you can see, it gave me, certainly, here is a suggested structure of a thesis on neural architecture search. Introduction, definition, overview of neural architecture search, motivating for use neural NAS, research question. It also knows that neural architecture search is called NAS, or the acronym of neural architecture search is NAS. It's not that straightforward to know, even though here it's like just taking N, A, and S, but it's not that straightforward. Sometimes it's complicated. Research questions and objective of the study, a brief overview of the rest of the thesis. So basically saying what each chapter is about, overview of the related works, previous approaches, limitations. It's really great how it does that. Okay, so let's try what country is more likely to win the World Cup? And of course, you can chat with her in English, French, Arabic, whatever language you want to chat with her, and it will give you the best possible answer, which is really impressive. Oh, let me just maybe. So I just refreshed because sometimes it has a lot of requests and it goes to timeout. Okay. It is difficult to predict which country will win the FIFA World Cup, as the competition is held every 4 years and involves teams around the globe. Okay. The World Cup is a highly competitive and unpredictable event, and many factors can contribute to a team's success or failure. Some of the top contenders in recent years have included Brazil, Germany, France, and Argentina. So we don't really know which one will win. Okay, so if you want to test it or try something else, just let me know. In the meantime, we'll go back to the slides. And yeah, so basically, this is really impressive. It can give you like a summary of whatever you want. It can give you even like, okay, I want to explain this concept. Can you write me the speech of my video or the speech of my presentation? It's also like wrote me the speech of the presentation and I sent it to the Discord, the School of AI Discord. So you can also like, yeah, you can also try this. Justine, how about explain pseudo polynomial algorithm? Okay, let's try this. So basically okay, perfect. A pseudo-polynomial algorithm is an algorithm that has a running time that is polynomial in the size of the input, but not in the magnitude of the input. Okay, so basically it gave you all this explaining the algorithm. I don't know if I can answer and I'll send you this results. But basically, yeah, you can ask it whatever you want, and it will explain anything. I think, can it teach me how to do SFSD TP? I think SFSD is too old, even for this machine. No, it's just a joke, but I think it can, yeah, it can certainly do that. It can also like understand a code and explain why the code doesn't work. it gives like it's really impressive. If you can go through the documentation and try a few things. I don't know if it's if it is already available in Algeria, but basically when it is, you can test like several things on it, and it's really impressive to have these kind of models that can do this. So before starting chapter 3, as always, let's do a summary of what we did so far. So we know that deep learning models are getting bigger and bigger and require cloud-like resources. So these models are really big. We cannot actually implement Chat GPT on our computers. We need some sort of really big cluster that can help us do this. So it's really, yeah, these models are really getting bigger and bigger. And then the second thing is that finding the right architectures require tuning different hyperparameters. We have the training hyperparameters, we have the architecture hyperparameters, we have also the operation within the architecture, we need to tune them. So it's really time consuming, error prone, we can fall into some mistakes. It consumes a lot of resources and energy. So it's really frustrating to do the work of a machine learning engineer trying to find the best architecture. And also energy consumption is a really important objective. So we don't want our deep learning architectures to really consume a lot of energy. However, these foundation models are going bigger and bigger. So it means that they consume a lot of energy. So just imagine if I have like to do 300 hours of training, 300 years of GPU training in a cluster, that would require like a lot of energy to have a cluster that can do that in 30 days or like few days or a few months. At the same time, we know that researchers estimate that the human brain contains on average like 86 billion neurons and 100 trillion synapses. So our brain is bigger than any model we have out there, and yet it consumes only 20 watts. So subhanallah, this is really impressive. Like, how can we have this kind of models but also have this kind of hardware that comes with these models so that we can use them in an efficient way? And we know that tiny hardware platforms, so I'm sorry. Sorry about that. Yeah, we know that tiny hardware platforms can achieve this energy reductions, but models are too big to be deployed in these architectures or in these hardware platforms. So we need to find a way to make these big models shrink and put them in a tiny hardware platform. So we call optimization to the rescue, and basically optimization will help us find the right, efficient, best, most accurate, fastest, smallest, and energy efficient model so that we can deploy it in an edge platform or a tiny platform. And by edge platform tiny, I mean like an edge GPU such as maybe Jetson Nano or Raspberry Pi, or even an Arduino or a small FPGA, a PINC, or any like small embedded device where we can put our hardware there or our model there. Sorry. And basically what we are doing here is that we are no longer, so I'm just like giving you the literature, what exists out there. So we have foundation model, we have these big models, but actually these big models cannot be deployed in these tiny hardware. And even if we apply some shrinking techniques or compression techniques, it stays really big. So we won't be able to put them in these tiny hardware. So what we are doing instead, we are trying to find the right architecture for these tiny hardware. And sometimes we, of course, use the parameters or use the pre-trained weights of these foundation models in our work in order to directly train these small models. So let me just explain what are the components of our optimization strategy. So basically, we have a search space. The search space contains all the architectures that we can think about. So all the ranges of hyperparameters, the operations within each place, etc. And then we have the search algorithm The search algorithm can be any optimization strategy that looks into this search space and tries to find the best architecture. Sorry about that. And tries to find the best architecture. And of course, to find the best architecture, it needs to evaluate its accuracy or latency or energy consumption. So we need another component that tells us, okay, this architecture is really bad, just avoid having the same architecture. And then we go to another architecture. Okay, this architecture is actually good, so let's do maybe another one that looks similar to this one. And if it's also good, then okay, let's continue with this road and try to exploit more this path. So we're actually in an optimization scenario where we have the trade-off between exploitation and exploration within our optimization algorithms. So yeah, as I said, the search space can be any architecture out there, a ResNet-like architecture, vision transformers, transformers for NLP, any model that we can like modify and try to find which one is the best inside this search space. The search algorithm can be an evolutionary algorithm, just like we studied in optimization. So we start with an initial population. We try to evaluate this population. If it's a good population, then we stop there. If it's not, then we do this selection, mutation, crossover, and we get back. We have a new population, so we get back around and we try to evaluate this architecture, etc. Or we can use another kind of algorithm, optimization algorithm, which is reinforcement learning. Basically, we train a controller to give us the best hyperparameters. And while doing this, we give it, the controller will give us one kind of architecture. We train this architecture to we evaluate this architecture, and based on the evaluation, we train our controller to generate better architectures. So we can have many more search algorithms. We can play with Bayesian optimization. So there are a lot of optimization algorithms out there. And at the end, we have this evaluation method. And this is the real problem with hardware-aware neural architecture search. And the problem here is that when we are we have an architecture in the search space. We are exploring the search space. We take an architecture, and then we need to evaluate this architecture. And as you may know, evaluating an architecture means training it. And if we train each architecture, let's say on CIFAR10, which is a really simple data set and a research data set, it's not at all a real world data set. So at the end, it would take us like 2 hours on an an A100 GPU. So it is really time consuming to train each architecture to know which one is the best. And there are several methods out there that rather than training the architecture, we will estimate the accuracy of this architecture. So one way to do that is, for example, training for 10 epochs and stopping there. Maybe just training for 10 epochs will tell us what kind of accuracy we will get at the end. But it's really not good. So one thing we thought about is to have surrogate models. And surrogate models are actually machine learning models. So it's like meta learning. You have a machine learning model that will learn to predict the accuracy of a model. So this surrogate model, given an architecture, it will tell you, okay, this one will be 93% on CIFAR10, for example. Or we can have a zero-shot method where you have, for example, an architecture A that we know about the accuracy of architecture A, and another architecture B. Let's say architecture A is a foundation model, for example, just to get you to link the two things together. So if A is a foundation model, and I'm going to compare B to A, and for example, I can compare the features, the extracted features. If the extracted features are really similar, then I can say this is similar to A, so it's going to have maybe 93% accuracy. And another way to do that, which is really interesting, is that to have So it's used actually for search engines. So for example, Google do that to classify or to rank the architectures, and we can rank the architectures from the best one to the least best one. And this is using the learning to rank theory. I'm just checking the time, and I saw that I consumed a lot of time. Okay, so I will be quick. I only have like the two slides, and that's it. So basically, some of the results that you can find here in this graph is that, so we have the handcrafted architectures. These handcrafted architectures are really big, and they have a really good accuracy, but they are really big. And then you have the hardware-aware NAS architectures in green. They have a not so good architecture, but you can see that they are getting closer to the handcrafted architectures. So we are getting closer to what we want, but there is still there is still need for research in hardware-aware neural architecture search to get it closer to these big ones and best ones. At the same time, the hardware-aware NAS architectures are really small. If you can see, comparing the round or the circles out there, the green ones are much smaller than the blue ones. Okay, so just to conclude, and I think I was taking questions while I was speaking, but if you have any more questions, please ask. So just to conclude, the use of tiny hardware will really help us decrease the impact of deep learning on climate change, especially, so as just to give you an example, when using neural architecture search and training each architecture, so we do that, but we train, we don't estimate, we fully train the architectures, we will emit more than 20 times more than the whole lifetime of a car. So if just finding the right architectures will emit more CO2 than the whole lifetime of a car, it's really a problem, and we really need to make sure that we can use these tiny hardware and alleviate the impact of deep learning on climate change. And one way to do that is to use these hardware-aware neural architecture search to find the really small architecture and the inefficient architectures. And many other researchers are thinking about what kind of strategy that we can do to use really efficient hardware and still use deep learning, because we still want to have this capacity, or these smart chatbots and smart creators and language models, etc. So we still want to use them, but we want to use them in an efficient way. And this is why we need to combine hardware-aware neural architecture search, or the use of tiny hardware, with these foundation models at some point. Okay, so yeah, thank you for your attention. I'm just going to check if there is any question. Just made a mistake. I have image detection and recognition. Okay, that's why we use YOLO. Okay, I understand. So yeah, YOLO is a good one for image detection and object detection and recognition. It's good. You started from, I think, the best models out there, which is version 5 and version 7. So it's good. But it depends on what kind of hardware you're targeting. So if you're targeting a resource constrained hardware like a Raspberry Pi, or a small, like a resource constrained a low resources device like an Arduino, a Raspberry, a smartphone, YOLO is the best. If you have like a GPU and you're trying to do that in a larger network, so for example, in an autonomous driving car, we wouldn't use YOLO for detecting the objects. We want something really fast because we have a GPU that is really big. We already we have like I believe we have 800 and V100 in an autonomous driving car. So we have really, we already have the resources to execute a higher accuracy model. So YOLO is good for resource constraint, but if you can, but if you can use like more bigger models, you can. So I think I'm really on the time, like 45. Sorry about that. I took a lot of time, but I hope I gave you a lot of information. And if you have any questions, I'm here to answer them even in the comments.
Thank you so much, Hajarullah. Your talk was really fun and amazing.
Thank you.